Hello, everyone. Welcome to Theo-MathProblemSolver. And I'm excited to take you through the journey of PDEs and some other interesting, applications. In this very section, I want us to solve more examples relating into some properties of some, linear operators as far as, other related content, contents are concerned. So please stay with me and even as we go through this together. And I want to point out that in case you have not subscribed to my channel, please do so, and also like, comment, and share this quality content to other colleagues of yours as well. And then, I mean, the whole point is for us to demystify, the myth around mathematics. All right, so stay with me even as we do this together. All right, so the first problem of the day is that I want to prove that this particular PDE is linear. How do we do that? How do we prove that this is linear? So proof. So we want to show that this is indeed this particular PDE is linear. And in our previous episode, we laid down the foundation for linearity, or in terms as far as PDEs are concerned. Okay. All right. So the first thing to do is that we want to assume that we have two functions. Okay. So suppose that U and V are some functions. U and V are some functions. Okay. And C is a scalar. So as a scalar, I just mentioned, just like a constant, scalar is just a constant, okay? Or any real number, okay? Very important. All right. So on that note, we said that the first property is that, so if you have a linear operator, let's call it L, we said that if it acts on the sum of the two functions, then we said that we should get something as this, okay? That's what we said the last time, okay? Good. And then the B part is that when the operator acts on the CV, we should have what? We can pull out the C, then we have what? LV. Okay, so you can also use U. It holds for U as well. So let's take note of that. So how do we leverage such properties to solve the problem? Now let's go straight to the point. So now we know what we want to do. So let's go straight to the point. So remember that we are given this problem to solve. So what we are going to assume is that suppose we have some function f, okay? Suppose we have some function f, so some solution f, okay? Suppose that f is a solution. Then it means that if we operate it on this, then we should have, now remember that we have given this particular proposal, we can, if we operate the L on, or if L act on that particular solution, which we said some function is, which we call it the f, then we should have ln of x multiplying t squared of the partial of f with respect to the t, okay? And then the sine of x plus t, then the partial of f, the second partial, because this should be second partial of with respect to x, then plus what? X what? F. So our U is now like more or less like, your U is more or less like your F, okay? Good. So let's take note of that. So if that's the case, then I now utilize the first property, if I want to utilize the first property, it just means that wherever I see F, I should replace it by what? I should replace it by U plus V. Okay, if that's the case, it means that wherever I see U plus V, I should replace it by, wherever I see F, I should replace it by U plus V. Okay, very important. So let's move on. So on that note, you're going to have the lane X multiplying T squared, and then the partial of U plus V minus sine of X plus T, the second partial of what? U plus V, then X multiplying u plus v. Okay. All right. So let's do our distribution. Remember the differential operator is distributable. Okay. So we can do the distribution, and by doing the distribution, we should have ln of x multiplying x, t squared. Then we are going to have what? The partial of u with respect to t plus the ln of x multiplying t squared of, and then the partial of v with respect to t minus the sine of x plus t, the second partial of u with respect to x squared minus sine x plus t multiplying the second partial of v with respect to x. Then finally, we have to also distribute, we also have to distribute that, and that gives us what? xu plus what? xv. So let's take note of that. Very, very, very important. All right, so at this point, what we can do, we can switch back to the way we used to do it. And by doing that, we should have what? The ln of x that u t plus the ln of x t squared v of that then the sine of x plus t plus x u x v. Good. So now that we have this, now let's try to group the u's. Okay, the u's. Let's try to separate the u's from the v's. So we have one u here, another u here, and then another u here. So let's try and put them together. So by doing that, we're going to have the u's to be the ln of x multiplying t squared u of that plus that is minus the sine of x plus t u, the second partial of that, then plus what? Plus xu, right? Now we are left with the other part of that, and then we are left with the v part. Now let's try and group the v. So we have one v here, another v here, and then another v here. So let's also do the grouping of it as well. So we have the ln of x t squared partial v with respect to t, and then we also have final the sine of x plus t v xx then plus x or v. Now over here, what can we say about this? So this becomes your L hot, since everything in terms of u, this becomes your L u plus. Now over here, it is over here, we see that it is just the same as what? Over here, it's just the same as the given problem, right? We see that what we have underlined here is just the same as the given problem. So this becomes your LU, and this is also similar. So this becomes your L what? Your LV. So now you've been able to prove the A part of the law. Now we need to look at the second part of the law. And the second part, what does it say? The second part of the law. So let me use a different pencil. So the B part say we want to prove that your L when the operator act on C, U, or V, we should have something like this. Okay, good. So on that note, how do we prove this? Now on that note, if I have CV, it just means that wherever I see U in the given problem, wherever I see U, I should replace it by what? CU or CV, okay? Good. Over here using V, so we will do that one. So and I know we are going to have x, the lane of xt squared, and then CV of that, then minus sine of x plus t so I have, let me use my pencil. I have CV second derivative, okay, plus x, then I replace the u by what, CV. Is that okay? Good, good, good. Now, when I do my distribution, I'm going should have, then I bring my C back, I should have, over here, I see that the C is common throughout, so I can bring out my C. And that, is that okay? By bringing out the C, I'm going to have something as this. What can we say? What do we see over here? This becomes my L hot, my LV. Good. So now we've been able to prove we've been able to prove that indeed, you've been able to prove that indeed the PDE, this particular PDE is what is linear. All right. So I believe at this point we all understand it. And if you're new to this channel, I want to point out that this is one of the best channel ever to work on calculus, ordinary differential equations and partial differential equations. And if you have not subscribed, please do so. Like my comments, comment, click on the notification button so that anytime I release new content, you'll be the first to receive that. And also, if you are do well to share this content to your colleagues, to your loved ones. So let's help, demystify the myth around mathematics. All right, thank you. Let's move on. Now, I have some few remarks to make. And this remark is very, very, very important because we will be using that to solve problems as well. So I want you guys to really take your time to really understand this particular remark. So it's a remark, so let me write it. So all right, so this PD is called quasi-linear. It's called quasi-linear because now let me bring it back. I think that let me bring you back to what we've done so far so that when I'm referring to that, you would really understand that. Okay, so let's reflect on this given equation again, or this given PDE again. So we're going to reflect on that and see how best we can use that to understand certain things as well. All right, so now the PDE of first order only involve the solution functions and their partial derivative up to the first order. Okay, and this was the first example I explained earlier. Okay, very good. Now there are some few things that we have to take home, and the first thing is that a PDE is called quasi-linear. Okay, because the PDE given is called quasi-linear because the solution U appears in the coefficient AJ. So over here, we see that AJ over here, remember it's a function, AJ is a function, and we saw that the solution U appears in that particular function, okay? In that particular function, AJ, we saw that U appears in that particular AJ. And that same function is multiplying the partial derivative, it's multiplying the partial derivative. Okay, and that's what we said. This is a quasi-linear, PDE. Okay, very good. Now there are other interesting things that I want us to look at other interesting scenarios, because it's most PDEs are not always like that. Okay, so if it's not like what name do you give to that? So that's what I want us to also look at. Now, if U is not in AJ, suppose that U is not in AJ, okay, but it appears in C in a linear way, okay? So remember, this is your C, right? C is also a function, some function, which is composed of X and then the function U, or the solution U as well. If it just so happens that U does not appear in AJ, but this time around it appears in C in nonlinear way. What do you mean by nonlinear way? So U to the power 2 becomes nonlinear, okay? That's a quadratic, right? U to the power 3, U to the power 4, U to the power 5, U to the power 6, and all of that. U to some powers becomes what? Nonlinear, okay? If C happens to appear this way, then we say that then we also kind of say that we have a semi-hot linear, okay? And we also, if you have C to be of this form, because we have e to the power U, this is nonlinear, okay? So in such a case, we said that the PD is called semi-linear, okay? Let me take it one more time, that a PD is called quasi-linear if U appears in the coefficient of AJ. Is that okay? And it is multiplying the partial derivative of U. Is that okay? Good. And we also went further to exploit that sometimes it's not always the case that U has to appear in AJ. Okay. There are instances where it will appear in the function C in a very nonlinear way. And I also want to mention that U to some powers greater than 1 becomes nonlinear. So an example is this particular one. Okay. And then this also as well, because e to the power U becomes nonlinear. Okay. And we said that in such instance, we said it's called then nonlinear. Okay. Sorry. In such instance, we said it's called semi-linear. Okay. It is called semi-linear. So let's take note. These are very, very important and fundamental stuff that I want you to really have them in mind. Okay. All right. All right, so let's get the remark too. And so now there can be another interesting stuff, okay, where always U may not appear in C in a very nonlinear way. Okay, it can be linear, right? And so we over here I want to point out that if it happens that U does not appear in AJ, but then it appears linearly in C as this, okay? As this, then we claim that such an instance is called a homogeneous linear PDE. Okay, that becomes a homogeneous linear PDE. So please let's take note of that. Now, what if it appears in C in a different way? Okay, what if it happens this way? If U appear in C, which is a function like as this, then we claim that such a PDE is called an inhomogeneous, or some books say non-homogeneous linear PDE. Okay, that is inhomogeneous or non-homogeneous linear PDE. So let's take note of that. Okay, so let's take note of that. If we add some constant term to this, then we get the inhomogeneous or a non-homogeneous linear PDE. So let's take note of that. Very, very important. At this point, I also want us to look at some other interesting stuff that I believe on our way to understand other interesting subsequent content that would really help you a lot, because you may get to a point where you may not really have to go back to revise, but because you've been able to understand this, it'll be easy for you to rely on them and then apply them. We go straight away, okay? Instead of always going back to previous episodes. All right, so a fully nonlinear first order PDE has the form this, okay? Now we said that search is defined this way, okay? So we said that this is the gradient of U. We call this one the gradient. So let's take note of that. We said that this becomes when we have something as this, we said is the gradient. We said is the gradient of U, and we define it this way. Is that okay? Good. Here, the F is a given function that is defined on some subset of R to the power, or R 2n plus 1 with some values in the real number. Okay, don't worry about this. We would look at some few examples so that you'll be able to appreciate that. All right, let's jump into some interesting problems. I believe these problems can help you to also get a good grades, help you to get all your full marks in your quizzes, in your super quizzes, exams, and then your finals as well. But before we jump into that, I think there's a way we can also use to classify PDEs. Okay, now so let's look at that. All right, just a quick one also as well. We also said that already we have already introduced this, but I mean, just for you to appreciate what we've done is just probably like a recap for you guys. And that the partial of u with respect to x can also be written as this. And the second partial of u with respect to x can also be written as this. The first partial of u with respect to t can also be written as this. And the partial of uxt can also be written as that, and so on. Okay. And then we call this one the Laplace operator. So I want us to take notes. So anytime I say the Laplace operator, I mean to say this. Okay. So this is the Laplace operator. So the Laplace operator is this. Okay. So this becomes your Laplace or Laplace operator. So let's take note of that. And I would say that is the most physically, important differential operator, which is giving us that. Okay, very important. So let's take note of that. Now, the PDEs of second order. So with this one, we also want to point out that these PDE also involve the solution functions and their partial derivatives up to order 2. Now we've already explained what an order of a PDE, and we said it's the highest derivative of any given equation. Okay, we said the order of a PDE is the highest the highest derivative in a given equation, right? Good. Now, how do we classify, second order linear PDEs? So a second order linear PDE in two variables, let's say xt. So the xt are independent variables. Okay, in an equation of this form, where A, B, C, D, E, F, G are just constant, okay, or scalars, or specified, functions of the variables xt. Now, such equations can be classified into various types based on the coefficient of A, B, C, A, B, C, okay, and others as well, or just A, B, C because we're going to use a discriminant. Now, we claim that such a PDE is elliptic if the discriminant is strictly less than 0. So we refer to this as your discriminant. This is what we call the discriminant. And we also say that the PDE is parabolic if the discriminant is 0. Okay, and we also claim that the PD is hyperbolic if the discriminant is positive. So let's take note of this. We'll be looking at one or two examples on all of these as we move along. Okay, so let's take note of that. At this point, if you have not subscribed, please do so. Click on the notification button so that anytime I release new content, you'll be the first to receive that. And also, if you have not shared this content with your colleagues, with your loved ones, please do so that we can help spread, mathematics and help demystify the myth around mathematics. Some are of the opinion that mathematics is for the geniuses, mathematics is not creative. But is it really the case? Never. Math is not so. Math is creative. Math is creative. Math is creative. Math is not only for the geniuses. So please, quality and powerful, platform as this helps a lot to help demystify those myths. So please always bring in your friends, spread this good news, and let's help as well. All right, thank you. So we can just use this as an example, as a guide to classify that. Already it has been classified, but you can look at, the tools that I've laid out here to help, do the classification. Then if you have any questions, you can put in the comment section, and I would doer to check that. Okay, very good. Let's move on to the next section. So over here, we are given this particular problem to solve. It says that for each of the following equations, state the order and whether it is semi-linear, quasi-linear, fully linear, linear non-homogeneous, or linear homogeneous. So we wanna state. So the first thing to do is that we wanna state the order. So what is the order of this? So the order. So what is the order of this PDE? We said that the order of a PDE is the highest derivative of in the given equation. So what's the highest derivative? It's 2. So the order of this PDE is 2. Good. Let's take note of that. And we want to determine whether it is semi-linear, quasi-linear, fully linear, linear non-homogeneous, or linear homogeneous. So what is the type? So this PDE is what? What can we say about this? Remember, we said that with a quasi, we said that with the quasi PDE, we said that if AJ contains the solution U, then and it's multiplying the partial derivative of U, then we claim that it's quasi. But over here, we don't have that, right? We don't have that. We don't have any solution U multiplying the partial derivative. So on that note, quasi derivative is out. We said that out, or it is out, right? What about the semi-linear? The semi-linear, with the semi-linear, we said that if the solution U appears in C in a linear way, then we said that it's what? Semi, right? So this means that this PDE is what? Semi-linear PDE. Is semi-linear, okay? So it means that this PDE is semi-linear. Is that okay? All right, very important. So let's look at another PDE. Let's see what I can get you. Very interesting ones. What about the partial derivative of ut, the partial derivative of u with respect to t minus uxx plus e to the power x multiplying u equal to 0. What then becomes the order of this? And mind you, we said that the order of a PD is the highest derivative. What's the highest derivative over here? Is what? Is 2. But is it semi-linear, quasi-linear, quasi-linear, fully linear, linear non-linear, or linear homogeneous? So the PD is what? Is what? It's linear, right? We said that if the function C contains U in a linear way, we said that it is what? Linear. So this PDE is what? Is linear. Good, good, good. My students are so good. All right. Now let's look at the C part of this problem. So let's look at the C part. So the C part, we have U TT minus U multiplying U XX plus X squared equal to 0. What is the order of this PDE? So what's the order of this PDE? That is what? 2. And the PD, this particular PDE is what? Is it quasi-linear? Yes, this particular PDE is quasi-linear because the AJ contains U, which is also multiplying. The AJ contains the solution U, which is also multiplying the partial derivative of U. So now this becomes what? A quasi-linear. Is that okay? Very important. What about the D? So we have UTT all squared plus UXX all to the power 2 equal to e to the power x. What is the order of this? The order is what? Is 2. And what about the PDE? The PDE is what? Is it linear or nonlinear? We see that the partial derivatives are squared, which makes them nonlinear. Is that okay? So we claim that this is nonlinear, okay? So non-homogeneous. So this becomes non-homogeneous, okay? Nonlinear, okay? This becomes non-homogeneous nonlinear. And at this point, if you have not subscribed, please do so. Like my content, and then also help spread this good news by sharing the content with other colleagues, with your loved ones, and let's keep the this information spreading. And then also I want to point out that in case there are certain questions you may want me to help you out, just put in the comment section and I will attend to that. At this point, let's take a break and we'll come back. Stay blessed.